this is the situation before impact, and I've calculated the total momentum of this system, the A and B block system prior to impact. So the total momentum of this system, and I can put a P sub T sub before here if I wanted to. It's going to look messy though. It's just the momentum of A plus the momentum of B. We're in one dimension, so we can just add those together without any vector issues. It's 22 sec newtons. You do the same over here. Remember that we're talking after impact. After impact. Momentum of A is, I'm not going to do MAVA. I'll just do is 10 times V, sec newtons. Momentum of B is equal to 40 sec newtons. Question, why didn't I put the minus in front here? Well, mass is a scalar, and we don't really know what the direction of the velocity is. We're going to find that out. So I don't know whether V is minus or plus at this stage. Of course, you calculate the total momentum in one dimension. It's very easy. It's just 10V plus 40. That's sec newtons. What's the next step? Yeah, solve for V, but there's a step in between. There's a sentence you need to say. Yes, that's what I was looking for in particular. I was looking for this by the, I'll just say C of M, C of P, by the conservation of momentum, the total momentum of the system before is equal to the total momentum of the system, blah, 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 after. Okay? So that's the total momentum of the system before is 22 sec newtons. The total momentum of the system afterwards is 10V plus 40. I'll equate those. 22 is equal to 10 times V plus 40. V equals minus 1.8. It's a speed, meters per second. Don't forget your units. And the other class has this question. If I've got a minus in front there, am I allowed to say this? Am I allowed to say to the left, or they're talking in east and west, aren't they? So yeah, you can. To the east. To the east always means to the east. Doesn't matter whether you put a minus in front of it. The minus is a mathematical term, and this is a written term. They can't be mixed. And so if you say minus 1.8 meters per second to the east, it still just means to the east. But theoretically, you could leave it as that. I'd clarify it though with this to the east. Oh, sorry, it's west. West. East is that way. West is that way. Yeah, sorry. To the west. If we remember, you guys all remembered it. Nobody picked up on it. To the west. Another problem. How much room have we got? What is the problem? This one's for you. And I'll cut all of this out here. Actually, no, I won't do that. I'll go to a new page. we set this up at the last school that I was at with an air rifle. I suspect it's a something that we can't do. We're not allowed to, but that was in the country and different rules out there. So before firing, here's our system. It's the bullet and the gun system. And after firing, still the bullet and the gun system. They give you the masses, and they give you the speed of the bullet afterwards. What's the speed of recoil of the rifle? What does the rifle do? It goes left, of course, or it goes towards or to the west, or towards the person who's firing the weapon. How do you calculate this? Of course, is 0. And so, well, what do we have as a total momentum on the left-hand side? 0, yeah, that's right, 0. That's right, mate. Yep, no worries. Total momentum equals 0. And momentum of the rifle equals 5v sec-newtons. Momentum of the bullet equals 0.05 times 500. Thank you. 25 sec-newtons. Total momentum. Yes, we know that. 25 plus 5v and sec-newtons. Which we're going to say, of course, is by the conservation of momentum. Velocity is 5 meters per second. And the book says it makes a statement. Oh, sorry, 5v equals. I've jumped a step in here, and it's got me unstuck. Be very careful with that. 5v equals minus 25, of course. So v equals minus 5. It gives us a direction. Minus denotes to the left. So, therefore, the rifle recoils at 5 meters per second. 5 meters every second is pretty quick, yeah, but it's very, very quickly absorbed by your shoulder. If anybody's ever fired a rifle. Nope. In the where I'm coming from, in the country, every student in the class would have fired a rifle, no question. Okay. Any questions about that? We'll move on. We'll do another problem. Here's another problem here. This is a two-dimensional collision. Now, key here is you need a vector diagram. What's the total momentum of the system before equal to? Or what's the total momentum of the system after equal to? It's equal to the total momentum of the system before, so you just need to calculate the total momentum of this system using vectors, using a vector addition. Okay, so let's say what we do know. momentum of A is equal to, I won't say MA times UA, MV, P equals MV, 4,000 times 15, which equals 60,000 sec newtons. Most people should have been able to get this far. 1,000 U sec newtons. And they say that, so a truck of mass 4,000 kilograms travel. Oh, sorry, yeah. This is, I've got that in 15 meters. Oh, that's 15 meters per second. So they've changed the, sorry, yeah, I skipped a step. I'm just reading through it now. They've changed the 54 kilometers per hour to 15 meters per second, divided by 3.6. You're not going to get the unit sec newtons if you don't use this in meters per second here. Collides with a car of mass 1,000 kilograms travelling north. After the collision, the two vehicles lock together and slide without friction in a direction east 30 degrees north, so off in this direction. So they're saying that this is one mass now here, and they go off in this direction. What was the speed of the car before the collision? This sort of situation comes up often in modern day calculations of what happened in accidents. You'll have seen where an accident has happened on the road. The police will paint marks where they think the cars travelled, where the impact occurred, where the cars ended up, so that they can remove the cars and let the traffic through, and then the physicists or the police that are also good at physics can come in later and calculate or get all the information that they can. And why would they do that? Well, they might say, this guy in car B, I'd say, I was only doing 60. And that truck came out and we had an accident. So I was obeying the law. The truck was obeying the law. But this horrible accident happened, and the truck says, no, he was going much faster than that. And they say, well, can you be sure? They don't know. So they do a calculation. They do a quick calculation. And they have to take into account, of course, friction. But they've got lots of experience with this, so they can do that. And it's admissible in a court of law. Not as much detail as we're going to calculate here. They can't say he was doing 121.3 kilometres per hour. That's just not possible with the conditions of the road, the quality of the tyres that were on the car, all sorts of things that were going on. There's so many variables, but they can say we're pretty sure as professionals that he was doing greater than 60 kilometres per hour. Therefore, before the accident, it appears as if there's lots of evidence to support that he was breaking the law, and that goes against them in court. Okay, so let's draw a vector diagram. Is the first thing to do. Travelling 60,000 north. So 60,000 sec newtons east. I've got to choose this guy. East. And travelling north, 1,000 kilograms travelling north. We don't know what the length of this vector is going to be. I'm just going to draw it as a similar length. And then we have to say, I'll draw my arrows to show the direction of those vectors. And I'll label them in a second. I'm just going to draw the resultant so that that's clear now. There's the resultant. Okay. With its arrow. Vector addition there. What are we looking at? It's a right angle triangle, of course. With this is 60,000. And this is 1,000 U. And we know that this is 30 degrees here. Because this is the total momentum, isn't it? That's the total momentum beforehand. But it's also the total momentum afterwards. So I can say That's 30 degrees there. Okay. How do I find the length of this vector? Is that what we're trying to find? The velocity of the two? No, we're trying to find this u, aren't we, here? So what do we use? Tan 30 degrees equals opposite 1000 u over adjacent 60,000. U equals 60 tan 30. Which equals 34.64 meters per second. What does that mean to most of us? Nothing. The police will, they'll say, well, you cover 30 meters in a second. You've got a fair idea about that, but we have more experience if we do this per kilometers per hour. Book says 124.7 kilometers an hour. Was he breaking the speed limit? Yes, he was. It looks, there's lots of evidence to say that he was, okay? They can't say conclusively, but there was a bystander who said, I think he was doing about 100 kilometres an hour, maybe more. The police did the calculation. It's reasonably conclusive. We have a conviction. Straight to jail. Thus the car. Allegedly entered the intersection at about 125. And of course, the defendant's lawyer's not going to be happy with that, rounding it up. But that's okay. What did I do next? Any questions about that? Good. Multi-image photographs. How much space we got? None. I'm not going to do this problem here. This problem, we'll do one. Oh, actually, that's what we'll do. We'll do one out of your homework. This is an explosion problem, and there's no problems in any of the exams that I've seen so far where they require identities in mathematics that are anything other than describing right-angled triangles. So it's only Pythagoras or SOHCAHTOA that you're going to be using. So I remember the first time I taught this, I went through this example, and it took half an hour, and at the end, all of the students were pulling their hair out, and it was a big mess. They couldn't believe that physics was so hard. So we won't do that. We'll do this. Here's a problem for you. Stationary object of mass 7 kilograms explodes to form 3 fragments. A of mass MA 2 kilos, B of mass B 1 kilo, and C of mass C 4 kilos. Fragments move in directions shown in the diagram below. A is travelling at speed 2 meters a second, B is travelling at V meters per second, and C is travelling at 2 meters per second. Assume no external forces are acting. The question says, State the total final momentum of the 3 fragments after the explosion. 0. If it was 0 before, it is 0 afterwards. Oh no. I pressed too many buttons. Oh, and then in the space, draw a clearly labeled diagram showing the vector addition of the final momenta, PA, PB, and PC. And then find the magnitude of the velocity V of fragment B. So I'll write that here. Find V. Have a go at that. I shall do this in pink, works across the colours, or the black and white. Okay, so B is kind of in that direction there. A in that direction, and C in that direction. And make sure I have arrows. This diagram is not to scale. Make sure you label it. This is, of course, momentum of B. This is, of course, momentum of C and momentum of A. And this, being that B and A earlier were right angles. Yeah, that looks like a curve. That's right, it's better. They're still at right angles. We have a right angle triangle. Momentum of A equals 2 by 2, 4 sec newtons. Momentum of B equals 1V, or V, sec newtons. And C equals 8 sec newtons. V squared plus 4 squared equals 8 squared. Pythagoras. V squared plus 16 equals 64. V squared, or V equals square root of 48. Which equals 6.93, thank you. 6.93. It's a speed, meters per second. Does that sound reasonable? Yes. We're looking at other speeds of 2 meters a second, 2 meters a second. C's a little bit bigger, almost 7 meters a second. And that's a V, but they actually asked find the magnitude. I think it was. So you just had to write the actual magnitude there, the speed itself. Another problem here. What I'm about to show you. Any questions about this one before we go on? They're easy when I show them to you, aren't they? Those people that are having difficulty. Some people, yeah, some people will. I expect that. That's okay. Well, this is the homework. I don't want that anymore. That's one of your homework problems. Here is, no, it's back here. This guy. Multi-image photographs look like this. You might have seen one before. Is there anybody that hasn't seen one before? All seen one? Good. What's going on here? Well, if you can imagine that this is puck A moving on an air table with very little friction. And this is puck B moving on the same air table with very little friction. They collide at this point here, and B goes off in this direction, and A goes off in this direction. It looks as if A isn't as massive as B, and in fact that it says it here. B is 3m kilos and A is just m kilos. So B is 3 times the mass of A. Confirming momentum is conserved from a multi-image photograph. Show that momentum is conserved in the multi-image photograph of a two-body collision. What are we looking at? Why have we got so many pictures of the same puck? You could imagine there's a camera set up here. If this were a photograph, and these photographs are possible, there's a camera set up here, and the camera has a long exposure, so the shutter just stays open, and at the same time there's a strobe flashing with regular frequency. On, off, on, off, on, off, on, off. And every time it flashes, you get an image of the puck where it is at that time. And so which puck is moving faster initially? A is moving faster initially, and we can tell because it's covering more distance than B is in the same amount of time. Okay? So how do we show vectorially that momentum is conserved in this diagram? It's not so hard. Let's use the diagram itself. I'm going to draw some lines here on the diagram. I think you guys have a problem like this in your homework somewhere. I reckon. I'll draw the initial vectors in red. I'm going to go from the center of this puck to the center of this puck. What am I going to do with B? I'm going to go from the center of that puck, not to the center of this puck. I know some more information. I can go to the center of this puck. What have I done? It is, isn't it? If I'm talking about a momentum, if I'm talking about this is the, that's a line. This is the momentum of A, and this is the momentum of B. Then, I better draw that line again because it's a terrible line. And this is the momentum of B. Then I can take into account the masses, can't I? And MB is 3 times the mass of A. So I can go over 3 different images. Same amount of time between each image as there is between that image and that image. And then I've just extended it out by 3. Now, I've got to put my arrows there. So show the direction. When you draw vectors, don't forget your arrows. Oh, yeah, I just made the line thicker and then I made it thinner again, didn't I? You can still see that. Okay. So that's the momentum before. How do I show the total momentum vector? Can I add A to B, or B to A for that matter? I'm not going to add B to A because it's a bit messy and it sort of cuts across here. I'll add A to B. I'll take the tip and I'll make it parallel to A and about the same length. There. Oh, I didn't want to do that. I keep forgetting that I've got to choose. Then I'll draw I'll draw another vector. What's that vector I just drew? What do you call that? It's the resultant vector, isn't it? That's the total momentum of the two-puck system prior to the collision, isn't it? This here, and I've got PB behind it, but it's actually it's total momentum. Total momentum of the system. What do we know by the conservation of momentum? That we should be able to equate the momenta here and the momenta here to form a vector that looks exactly the same length in exactly the same direction. So let's do that. I won't talk so much. A, of course, here, across one puck space only, and B, we're going to go across 3 again, 3m, mass times 3. And then I'll draw in my arrows, and then I'm going to add them. What will I do? It doesn't matter. I can add B to A, or I can add A to B, whatever you want to do. Last time I added A to B, I'll do it again. That's about the length and about the direction. Please, boys. Draw the arrow vector. We're going to draw a green vector in there too. The resultant, which looks like this. Vector addition of those two. What's interesting about that? It's a different color, but it's equal in magnitude and direction to the total momentum of the system beforehand. Okay? And that's how you do that. Total momentum of the system before is equal to the total momentum of the system after. So this is before, this is after. Key is understanding the multi-image photograph, and that 3m kilos and m kilos, you just go over everything else the same except for this mass here. So I'm just multiplying that over 3 images, where I only do it between 2 on this one. That's all there is to that. How much time do we have? Time for another problem, maybe.